Hello everyone. In this video, I'll be talking about a paper titled Finite Time Analysis of the Multi-Arm Bandit Problem. This was authored by Peter Rover, Niccolo Cesabianchi, and Paul Fisher. This paper appeared in ICML 1998, and this has a citation over 4,100 and above. Last time I checked was, I think, yesterday. Yeah. The overview of this video is to actually introduce you to the setup and the problem itself, and a short description of the algorithm and its result. And the most important part of this video is to get you a feel for the proofs to prove the result in this paper. Here UCB is expanded as uniform confidence bound. The algorithm in this paper was coined as UCB algorithm. Hence, I'll be using this short form a lot in this video as well. So with this, let's go into the setup. So we have K arms, the capital K arms. So think of K slot machines in a casino, 1, 2 through K, and each slot machine or an arm gives you a reward which is bounded. For simplicity, we can take it to be a value between 0 and 1. Every arm is having a reward between 0 and 1. And each arm has a distribution associated with it. So the rewards for arm 1 follows a distribution P1, and arm 2 follows distribution P2, and so on. And these are independent as shown here. We denote the rewards for arm I at time t. Time t as a random variable xit. So for any t, this xit follows the distribution pi, which is independent across t, the time as well. So this matrix is showing that, like, this is the time axis, time t, and this is the arm axis. So as time evolves, the rewards you would get are x11, and I mean the matrix shows it. So yeah, by construction, all arms rewards are independent. So yeah, this is the setup. Now moving on to describing the problem. So we have k arms, again writing it down. So let's suppose the best arm, or so to say, the best reward producing arm is somewhere here, denoted as star. So the goal is to find this arm with the maximum mean reward, which is shown in this star, the green arm. This is achieved by equivalently solving or minimizing a generic term called as the regret, which I'll define in a moment. So these arms, as we saw earlier, that they have the mean rewards to be mu I. I mean, ith arm has the mean reward mu I, or let's say this is the kth arm, so this is mu k, and so on. So this turns out this translates the green, the maximum translates to finding max over I mu I, but we do not have a knowledge about this mu I. So so a few assumptions in this problem. I mean, we can assume every arm has a different mean rewards. This is simply because if two arms have equal means, let's say mu1 is equal to mu2, then there is no better incentive to pull arm 1 when compared to arm 2. Like pulling both arms produces the same result. So that is the reason of this assumption. We also can assume that the first arm is the mu star. The first arm is the maximum rewarded arm. But this is only for the ease of the notations and the proof technique. And we'll define a new parameter called delta I, which is the difference between the best arm's reward and the ith arm's reward. This is delta I is positive because we have already assumed that mu1 is greater than mu I for all I. So now to define the regret. So the regret is, the definition is very natural. Is defined as So RT for any finite time t, define this regret RT as the summation from t equal to 1 to capital T mu of IT minus mu1. Or it should be the other way. Yeah. So here the IT is the arms which we would select the arm selected at time t. So as you can see from this definition that this regret is number one, it is positive because of the assumption. Number two, number one is it is non-negative, it can be 0. And number two is, since we are reducing the regret, our aim is to reduce the regret term, so the minimum value RT takes is 0. So this is achieved when we select IT as the first arm for all time t. But yeah, this should be learned in an online fashion, so hence we aim for reducing the regret. Sorry, I'll remove the clutter a bit here. Yeah, the aim is to reduce the regret as early as possible. So with this, we move forward a bit. So ignore this. Yeah. So here, I'll provide the link to the video of the converse result. The result, so here the result from Lai and Robinson, which was published in 1985, says that you provide me any strategy or an algorithm under the intent of minimizing the regret. They prove that asymptotically, this one, that the regret term is at least the constant times the log t. So we can't do better than RT is at least order of log t. I mean, this is an informal way of writing, and this constant O depends on the problem, like the rewards themselves. Yeah, I think that is it. So yeah. Mm, so that is why the intent of every algorithm now becomes to achieve this regret in terms of order of log t. And to add a fact, or to point out that this UCB algorithm actually achieves logarithmic regret for every time t. That is, it's not an asymptotic result, but for any t, UCB provides t to be less than order of log t result. So this is just an informal writing. Now moving on to the algorithm, UCB algorithm. Yeah. So the algorithm plays every arm once. So yeah, I mean, so UI had at time 1 will exist. Okay. Then for all time greater than k, I mean, since we have k arms, number of arms, it plays an arm it where it is defined to be as this quantity. It says we pick an arm I which maximizes this UCB I of t minus 1 term, and the averages mu i's will be updated after we play this arm it. Yeah, so this UCB I, the upper confidence bound term, is defined as the average term plus the confidence term. Here the capital T subscript I of t is defined to be, I mean, it just the interpretation of this term as how many times have you selected arm I from location 1 to t, yeah, number of times arm I is selected. And with this, the average term, the empirical average term makes sense, because we have picked arm I, ti of t many times until time t, hence the average term makes sense. So yeah, this is the algorithm, and the result, as I said before, for any t, finite rt is less than this term, to be exact. So these are the constants which was hidden. This one and these things were hidden in the order constant in this expression. So yeah, now we move on to prove this result. Yeah, the proof idea actually relies on two important facts. One is the concentration inequality, called as Hofting's inequality. There is Hofting's inequality says if we have random variables, independent random variables, z1 through zn, which are bounded between 0 and 1, then the probability that the sample average is, the difference between the sample average and its mean sample average differs by at least epsilon. It can be bounded exponentially with respect to the number of samples n. And this confidence term epsilon comes into picture in this bound here. And the second pictorially, the intuitive idea of why UCB achieves lofty regret can be expressed from this picture. So let's suppose we have two arms, the maximum arm and mu I, and suppose we start off our confidence terms from the right hand side here, somewhere here and here. As we collect more and more samples, we expect the arm the arm 1, which is the optimal arm, to be picked at least of the order of log t. Hence, this term goes to 0, and by central limit theorem, for example, central limit theorem, we know that mu1 hat approaches mu1. Yeah. So now moving on to the important part of this video. I'll be as complete as possible. So let me define a constant Li to be this thing. Oh yeah, I didn't explain how this definition came into picture. This is a simple derivation from the earlier version of RT. So earlier we had RT as the summation of t equal to 1 mu1 minus mu I t. Yeah. So we just separate out this summation with respect to the arm selected. So let this be like this, and we condition that IT is equal to 1. Which gives us 0 plus the other terms. IT is equal to 2 mu1 minus mu2 mu2, and this is nothing but delta 2 plus, yeah, as you have guessed, we'll get IT is equal to I, capital T, delta I. So now we have to remove this the dependence on T. I mean, you can actually see it here. So delta I can be moved outside the summation. Delta I T is equal to 1 to T, indicator IT is equal to I. So this is by definition is equal to Ti of capital T. Yeah, there is another summation which I'm missing it here with respect to I. This is with respect to I. And yeah, I had to be more clearer. So in the original definition RT, I had to so if you look at this, we have to take care of the mean part. So that is why we should have an expectation here somewhere. So this should take care of the definition, expectation. So no. So yeah, I had to like impromptu prove this result for the sake of the video. Yeah. So coming back to the beginning of the proof. Okay. So we look at this term in RT. So it can be written as 1 plus this term. This is because in the algorithm actually pulls every arm I once in the beginning, and after k plus 1 to t, it can be indicated in this fashion. Now we further split this term by adding these two exclusive events. The first term, if you see closely, says that for every t, the small t, the number of times this arm I is pulled is bounded by the constant Li. So which is also true for capital T. And if you see this term, which is again the summation of, it can be approximated to be the capital Ti of capital T. So approximately less than or equal to Ti of capital T, which is less than Li in this event. So this, for a more clearer argument, this just follows by pigeonhole principle. So maybe I'll include it at the end of the video. Let's see. The second term is what comes into here, what comes in here. So so the event BTI is defined here, which is nothing but IT. At time t, we are pulling arm I, and we have this event. So now, if we have this claim, if we can prove that this is true, this claim is true, then from here it directly follows that the UCB result which I presented earlier. So it all boils down to prove this claim. So now towards proving this claim, notice that we haven't used any tools which I mentioned earlier until here. So Hofting's inequality comes into picture for this term. That is because notice that we are conditioning on the number of times the arm I has been pulled to be greater than some constant. So that means Hofting's inequality, which is a concentration inequality, must help us to say that this probability dies down faster as Li increases. So that is the core of this proof. So for this, let us define this constant called Ct, s subscript ts to be in this way. So now for any arm in this 1 through k, this probability event, so from definition, mu I is this one, the sample average, and the true mean of the reward is mu I. Yeah, we bound this probability like this. So this is directly, this follows directly from the definition. Now from here to here, since Ti of t is random, but we know Ti of t lies between 1 and t, because there are only t many steps which arm I can be chosen. So conditioned on Ti of t to be equal to m, we can write it in this way. And this is an inequality because we are removing the condition. So this step is just union bound. This is a union event, and so we can shift it in terms of the summation. So here this step is the Hofting's inequality. Notice that by definition CTM can be written like this. So the m cancels and this is equal to e sorry t power minus 4, and there are t many terms, hence we finally get t power minus 3. So we did all this, and to summarize, yeah, we proved this, and yeah, by symmetry argument we can also prove this with the same similar steps above. Yeah, we did all this. Remember, our goal is to bound the probability of BTI. So for that purpose, we are gonna define a new event GTI like as follows. So yeah, so with these two results we can define GTI with guarantee that the probability of this event GTI is greater than or equal to 1 minus 2. This is because following reason. The first one here, this part let's take this part first. Let's call this event as E1 and this as event E2. So this one is E1 complement, right? Yeah, let me just verify. Yeah. And this part is nothing but mu1 cancelling of this delta I is less than mu1 hat plus ct of t1t, and this is the event e2 complement. So now GTI is equal to E1 complement union E2 complement. Sorry. It's an intersection. So probability of GTI complement is less than probability of E1 plus probability of E2 by union bound, which we already have proven that this is less than 2 times 3. And so this proves this result. So So now the claim is that for any suboptimal arm, GTI intersected with this event is a subset of this one. This observation is really simple. It follows like the as shown here. So by definition, GTI, as we defined earlier, and this is mu1 again. So if this is true, implies this part, since we are running our algorithm until capital T, so the lowercase t is less than or equal to capital T. Hence this implication. Now these two are equivalent, just rearranging terms. So now under this event GTI, we have that, it's just rearranging this term with this term, where we have added this part and subtracted this part. So this is just to bring in the definition of UCB terms here. So under this event GTI, this is true, and now this is nothing but 2 times Ct of Ti of t. So hence under this event this is positive. Hence, at time t plus 1, we won't be sampling arm I, because UCB one term is here, and we strictly know that UCBI term is less than this part. So the algorithm will not pick, there might be some other arms here which can lie here, but this I arm which you have considered in this claim will not be picked, and that is this event. So we have proved this. Now the claim is that the event bt plus 1I is a subset of this event. This is a simple observation. So by definition, bt plus 1 comma I is this part, and from here this part follows. And this is the straight set theory reason. Now we already proved that this is true, that the event GTI complement, the probability of it is less than or equal to 2 by t power 3. And from this and this, it is clear that probability bt plus 1 comma I is less than 2 by t power 3. And remember that summation of 1 by t power 3 from 1 to infinity is pi square by 6. So this is this result. And this ends the proof of the UCB result, that the regret achieved by this algorithm is of the order of log t for any time t. Yeah, the result, yes, this one.